Okay, so we got this set up here. Some sort of bar attached to a collar here that has another rod attached to it. Bars attached at the wall here. For this problem, what we're worried about is stress analysis at kind of this fillet here, A. And the load that is being applied is just 100 pounds upwards. So I kind of just resketched that here. So we want to determine what the stress state is at that filleted shoulder A at its critical point. We want to sketch the stress element at that point, determine our principal stresses, and then we want to say if the bar's cast iron ASTM 40, we want to figure out what that safety factor is. So at that cross section, when we have that load, this load here, there's basically three effects that are going to be happening. There's going to be a torsion effect caused by the moment about the x-axis. There's going to be a bending moment caused by the moment about the z-axis. And there's going to be some direct shear as well. So the bending moment, again, about the z-axis there, is going to be causing a tensile normal stress at the bottom of the fillet. Because again, it's kind of pushing upwards, it's pushing up on the end of the bar. So basically, at the fillet there, the top's going to be getting compressed, the bottom's going to be under tension. And since the tensile strength of the cast iron is a lot weaker than its compressive strength, it's 42.5 KSI versus 141 KSI, and again, that is from our Fundamentals Machine Component Design textbook, juveniles, taken from Appendix 3A. So here's the chart that we're using. Post that down here, or up here if we want, I guess. But yeah, so the tensile strength for that material is 42.5 KSI, and we are looking at 140 KSI for its compressive strength. So we're far more concerned about where the tensile strength occurs, for where the tensile load occurs. And then obviously both the direct shear load and the torsion are going to cause shear. So shear is not compressive or tensile. It causes either depending upon which orientation you're kind of looking at when you try to switch things back to your prime axis. So anyways, but that having been said, again, we've got our direct shear oriented vertically. So at the top and at the bottom of the of the object, or of the cross section, the transverse shear that's going to be causing that is going to be 0, because we've got our Q is equal to 0, and so we can neglect our direct shear effect there, the transverse shear caused by the direct shear. The bending stress is going to be equal to negative kt my over I. So again, we're used to the my over I. We're throwing in the kt there as well. We are worried about what our stress concentration factor is because this is a brittle material. And due to the fact that it's a brittle material, basically once it starts to crack, it's gonna go. So we can't we can't we can't have any localized yielding occurring like you can with the ductile material. Once it starts to break, it's breaking. So values we're using here. So the y, again, we're using a negative value for the negative 0.5 inches for the y, because we're looking at the tensiles occurring at the bottom of the cross section. So I'm just gonna sketch the cross section here. Let's see here. I think this is the y direction. This is the z direction. So we're looking at right here. So y is equal to, because the diameter of the the smaller section at that fillet is the 1 inch. The m, so for about the z-axis, we take the force in the y direction and cross it with the distance in the x direction. So that'll be our 100 pounds times the 11 inches. So again, we're going from here to here, basically. So that's this 9 inches plus this 2 inches. And then, of course, I is equal to pi d to the 4th over 64. Now, if you're wondering why I'm not using pi over 4 times r to the 4th, that's because once we start getting into stress concentration factors, we also start using this r to d ratio. The problem there is that the r there isn't the radius of the cross section. The r there is the radius of the fillet. So if we're looking at this little section side on, the radius of that fillet there. Oh wait, I realized that. Like that. So again, I think I should try to, for the rest of this course, try to start using only the D's for diameter instead of radius, because that pops up quite a lot. Anyhow, but obviously the value would be the same. So our I ends up being pi over 24 times 1 inch to the 4th. So that'll be 0.0491 inches to the 4th. And then our KT for bending is taken from the chart. So again, we've got our R over D. That's the 1/8 of an inch radius of the fillet there, divided by the 1 inch diameter of the smaller portion of the stepped shaft or stepped rod. So our R over D is 0.125. And then our D over D, our big D over little d, is 1.5 inches divided by 1 inch. So that's also 1.5. Yeah, so 1.5 inches, 1 inch there, and then of course our R's from there. So we need to figure out what those values are. So again, we go to our handy dandy textbook. So again, this is in juveniles. We can find our stress concentration factors. That's a table 4.35, or at least it is in the version of juveniles that I'm working with here. You might. I'm honestly not sure if it's exactly the same with the version that you're working with, but it'll do the trick. So this is the 4.35 gives basically the three types of stress concentration factors for kind of this type of geometry. The bending moment one's the first one, so this is the A. So the bending moment here can be found. So we got our RD value there. So basically 0.125. That'd be a line right about there. And maybe a bit more to the right. Right about there. And then the line that we will be using is that third one there, so the 1.5 D over D ratio. So we're looking at where these things cross. So yeah, right about here. So that yeah, that to me looks to be about 1.64, maybe a bit less, maybe a bit. Sorry, maybe a bit less than that, probably not more. But anyways, 1.64. I'm probably rounding up a little bit for that, but again, that's not exactly terrible. That's a more conservative estimate. So 1.64 is our stress concentration factor. And yeah, plug that in there. So our bending moment, negative 1.64 times 1,100 pound force inches times negative 0.5 inches divided by 0.0491 inches to the fourth. Again, inches cancels out that to the fourth to inches to the squared, so we end up with pounds per inch squared here. Plug everything in, and we end up getting 18.37 KSI. The torsional load is going to be shear, obviously. Torsion causes shear. And it'll be shear, and at that point, it's going to be shear in the ZX, XZ directions. So, we're looking at kind of the cross section on the X face. So this is the positive X face when we take that little cross section, and we're applying a twist like this in this direction. So that means that when we're looking at this point here, we're basically kind of pushing that face this way, which, as you will recall, that is the positive Z direction. That's the Y direction, that's the positive Z direction. So this will be a positive shear in the, a positive ZX shear. So, value of that shear, KT times TC over J, which again and we kind of plug in the values for the j there, ends up being kt times 16t over pi d to the third. And one thing that's helpful is that these charts in juveniles, the stress concentration charts, they give the nominal values there. So you don't need to bother looking everything up there, or remembering the formula. It's already just in terms of the load and the diameter. So 16t pi over d to the third. So our torque there is 100 pounds times the 12 inches. So that's this 12 inches right here. And what I do? There we go. And 100 pounds times the 12 inches, so 1,200 pound inches. Again, our R over D and our D over D stays the same, the 1.25 and the 1.5. So we just go back to our diagram here. This time we're using the C, because that's the one for torque. Zoom in here. So again, we are looking at about 1.25, and then okay, unfortunately we don't have the line for 1.5 here, so we gotta kind of make a best guess estimate. So the top line is 2, and the middle line is 1.2. So, and again, based upon kind of and we got a far wider gap between the 1.2 and the bottom line, which is 1.09. So again, it seems like these smaller, it's a bit of a logarithmic scale, I guess. So I'm gonna guess that it's probably not as high as this, but I'm gonna guess probably somewhere around there. So we're gonna go with 1.35. Again, we don't know exactly where that line is. I think 1.35 is probably estimating it a bit high, but again, that's not terrible. So going with 1.35, our tau ends up being 1.35 times 16 times the 1,200 pound inches divided by pi times the 1 inch to the third. So that'll end up being 4.25 KSI. So again, positive shear, because on the positive x face, it's causing a force in the positive x direction. So if I draw a stress element using the usual x, y, z orientation, this is what we end up getting. Here's our stress tensor here as well. And if we draw just obviously, if there's no stresses on the y faces, no stresses, no stresses on the y faces, then we're talking a plane stress element here. So, we can x direction this way, z direction this way, and we end up getting the tensile 18.37 KSI. We've got the shear of the 8.25 KSI, and then there's no normal stress in the z direction at that point. So you can use more circle, basically solving for our principal stresses. The average stress there is just going to, the average normal stress there is going to be the 18.37 divided by 2, or technically speaking, 18.37 plus 0 divided by 2. So that'll be 9.19 KSI. Radius there can be solved for by the 19.9 KSI squared plus the 8.25 KSI squared, and then take the square root of that. That gives us our value of like a radius on a Mohr circle of 12.35 KSI. So we can solve for our principal stresses there. So the 9.19 plus the 17.35, and then the 9.19 minus, plus the 12.35, and then 9.19 minus the 12.35. So that gives us 21.54 KSI and negative 3.16 KSI. So we know that this is brittle material, so it's basically kind of there's two failure theories that I'd kind of probably stick with. The simplest of them is Rankine, so the maximum principal stress theory. So that just gives us says that our safety factor is based upon our ultimate strength, again in tensile, divided by the principal strength in tensile. So 42.5 KSI was the tensile strength of this cast iron. So divide that by the 21.54 KSI as our tensile principal stress, our maximum tensile principal stress. Obviously, that we don't have a different tensile principal stress, but anyways, so that'll give us 1.75. There's also the simplified Mohr's theory. So again, that's the one that looks like this, and then just straight lines here. That's as opposed to the actual Mohr's theory, where it's not a straight line. It's actually a bit bowed out. But again, it's easier to calculate what your safety factor is for the simplified Mohr's, or just straight lines. So basically, in a situation like that, zoomed in too much. So basically, what we're doing here when we're trying to calculate what our so basically we are operating at a point that is, it's somewhere like here, I think. Because if this is 42.5, and this here is negative 140, our principal stresses are at 21.5 and negative 3.1. So, right about here, just below that line there. So when we're talking, I'm just going to I'm going to zoom in a bit more and redraw that so that I'm zooming in a bit more. And then let's say this is all kind of down here. So essentially, if we're talking just the Rankine theory, we're at an operating point like here, then the safety factor is just the ratio of this distance here. Actually, here, I'm going to put that in green. The ratio of the green line to the blue line. But the ratio of the blue line over the green line. Now, if we're talking the simplified Morse theory, then the green line that we use would be kind of this distance here, and the blue line will be out to the point where it intersects that line there. So it's going to be a little bit less. I'm going to save you the derivation of what how to calculate that. It's obviously a bit of geometry going on there that I'm sure most of you guys haven't touched since high school. But similar triangles could let you figure that out. But it ends up, you're able to calculate your safety factor there, as where the safety factor is the ratio of the length of those two lines. It ends up being when your first principal stress is positive and the second principal stress is negative. Positive, negative. 1 over the safety factor is equal to the absolute value of the first principal stress divided by the tensile strength, the ultimate tensile strength, plus the absolute value of the second principal stress. Sorry, yeah, the absolute value of the second principal stress divided by its compressive strength. Or realistically, I guess we didn't really need to use the absolute values there, as long as you also include the negative value on the compressive strength value here. So as long as this is going to be positive, and this value here is positive, this value here is positive, and this value here is negative, and this value here is negative, they both add up to positive things. So anyways, 1 over the safety factor here is equal to 21.54 divided by 42.5 plus the 3.16 divided by 140. And then solving for our safety factor, we end up getting 1.89. So that's slightly lower than what we see with the Rankine theory, and that's basically kind of accounting for the fact that when you have your principal stresses that are kind of different types, like if you have both compressive or both negative, then the largest one is the one that comes into play. In Rankine, in modified Moores, or so on and so forth, and in any of those. But if you have one that's positive and one's negative, then it ends up basically being slightly worse than the situation where they're both kind of the same type. And you see a similar effect with the ductile materials as well. If you have anytime you're having a positive shear and a positive and negative principal stresses, when you calculate your von Mises equivalent, it ends up being a larger von Mises value than it would be if you ended up having, say, the same values with both of them positive or both of them negative. But yeah, so yeah, safety factor there. 1.89 for the simplified mores. And I don't really, I don't think it's necessary to use any other failure criteria. Questions didn't specify, but I think that those two would cover anything. I would generally say simplified mores is what you should probably be using when not specified in any instances where you're using a brittle material. Yeah, and that's that.